Yeah, we can go ahead and get started. So yes, now we're doing fatty acid catabolism. So we're almost finished with all the major catabolic. Oh nope, we haven't done amino acids yet, have we? So we're getting there. Okay, so we've done sugars, a lot of sugars. Now we're working on lipids. Today we're going to primarily focus on fatty acids rather than some of the other lipids, just because. And then, like I said, I like to have fun with it in the sense that I say, do the lips to the hips, so on and so forth. Okay. On your own, make sure you look over chapter 10 about fatty acids from last semester. Like what does it mean to be a triglyceride versus the other things, like diglycerides and stuff. Make sure you understand what the glycerol backbone looks like, what a fatty acid is, and how they all come together to make these esters. Okay. So it's very, very important. Okay, so this is called beta oxidation. And when we're talking about the breakdown of fatty acids. Now, in order to go from a triglyceride to the fatty acids, you first have to have the lipases that break it down to make the fatty acid, just to get the free fatty acids. Then it's the free fatty acids that undergo this 4-step process over and over and over and over again, which I had previous students that made a YouTube video. It's very plain. You just hear them singing, and you see the words on the wall. But it is so repetitive that I usually show it because it gets stuck in people's minds over and over and over again. But it's the same 4 steps, same 4 steps, same 4 steps. And we've had glycolysis and gluconeogenesis, which, this was glycolysis, this was gluconeogenesis, but they're linear. And then that led into the citric acid cycle, right? And so now we're going to have beta oxidation. And beta oxidation looks something like this. That's supposed to be a spiral. Okay, but yes, it's a spiral. Because you start with something that's long and you break it down in groups of 2 to make acetyl-CoA. So every 2 comes off of it. It should be noted, and I've asked this question before and seen people get it wrong. Like whenever I said, what is a major energy source, biomolecule energy source for us in vivo? And so many times I see people say, it's sugar. It's sugar. Once again, it's not sugar. There are certain tissues, like the brain gets most of its energy, but by far and large, you get the most energy from your fats. Okay. And so, in fact, for example, the heart and liver gets 80% of all the energy from fats. Because remember, there were a couple of reasons that we talked about. One was the fact that we just cannot physically store enough glycogen and glucose on hand all the time. Okay? It's already partially used up, whereas what we'll see here is the fatty acid is essentially fully reduced, so that way we can go through get even more energy out of it, of the entire process. And also remember, it can do hydrogen bonding, so it's solvated, meaning it has water molecules bound to it, so it just weighs so heavy, whereas this excludes water, right? The fats exclude water, and so therefore they're dehydrated. Okay. And then finally, we have to talk about where acetyl-CoA ultimately goes. So acetyl-CoA is the final product. Where does acetyl-CoA from beta oxidation go to? Pyruvate. Right. Well, it's not to pyruvate, but it's right. It's the citric acid cycle, cycle, right? It's what hooks up. Pyruvate becomes acetyl-CoA. Why is it not? I know it's not responding. Close the program. Okay. All right. So, acetyl-CoA, so far we've talked about the citric acid cycle. We'll also talk about the formation of something called ketone bodies that happens by the liver. And that's what happens whenever you don't have enough glucose available. Okay? So, during times of fasting, especially during And it's a natural process, but it can go out of whack. Does anyone know what is the major health problems or psychological problems that someone can have that causes the ketone body formation to go out of whack and causes what's called ketoacidosis? Bulimia and anorexia is huge. So because during normal times of fast, and it's one of the reasons why you lose weight, right? You start to use up your fats. But yeah, they go out of. And then what's the other one that a lot of people don't even think about, unless you know someone who has this condition. It's been on the rise for several years now in the United States. And not cancer is due to our diet. Well, it can be obesity related. Diabetes mellitus in particular. Okay. Right, which can be obesity related, right? Type 2 diabetes. All right, and so we'll talk about ketone bodies later. And then also higher plants can use acetyl-CoA as a biosynthetic precursor, which we won't cover plants really, but that's just an FYI. All right, so what are some of the problems that we have with just using fats? Right. Okay. One has to do with its physical or chemical properties. Okay. And so we have the trans fats, and we'll go over those. Which are trans fats naturally occurring? No, / still asterisk. Okay, because they typically are not. Like the kind that we consume in our diet are not naturally occurring. We're going to find out they occur in your body 2 times, but they never leave. Unless, I guess, you are some type of mutant. And so during this whole process of beta oxidation and its opposite, there is a step where you have a trans fat, but it never leaves. Like your body holds onto it, doesn't let it escape. So that's why we say technically they're not naturally occurring. Another has to do with problems. Why is transport an issue?
They're so big.
Well, they could be big. What else? Because they're hydrophobic. So, you're going to eat lard, and it's not going to want to go through your bloodstream, and bad things can happen, right? And then, one problem is also a good thing, in the sense that it's relatively inert, which means it doesn't really react with things. However, that's also good, right? We don't want to be too reactive and have bad things happen. So that's why this is one of the problems we have, is you have to activate it somehow. You have to get it started, because otherwise you don't. And they have a lot of potential chemical energy, but they don't have a lot of chemical reactivity. Okay. So we have 3 sources for fatty acids. What's one source? Diet. Okay. Diet's a biggie. They call that one exogenous. That's the fancy term. What else is there? What else is a source of fatty acids? Right? So that's called biosynthesis, which is a type of endogenous. And the third source, so like I said, it's also endogenous, but it's kind of like pseudo-endogenous, I guess I could say. Where else do we get fat? Some of us have more of it than others. That's the stuff that's stored in the adipocytes. That's why I call it pseudo-endogenous, because it had to come from somewhere. And I think my slide's going the exact opposite. I think it's going to go 3, 2, 1, but you get the idea. There are three main processes, 3 main sources. Here, this is just an SEM of adipocytes. What's one characteristic of an adipocyte relative to regular cell, size-wise? Are they usually bigger or smaller? They can get huge. Okay. And does anyone else know? And we talk. By the end of the semester, we'll go more over adipocytes. But are they inert? Like, do they not? First of all, do they have a nucleus?
Yes.
Yes. Okay. Now, it's size-wise. What about mitochondria?
Yes.
Yes, little asterisk, because that's the whole difference between like white versus brown versus now that aren't there some kind of beige or whatever. I was gonna say taupe, but beige, right? But and that has to do with the mitochondria, by the way. And so once again, the white. I was gonna say blood cells. What the white adipose tissue has fewer versus those that are brown, and they also have a different type of protein in their mitochondria. All right, then we have the fats that are made in one organ. This is the endogenous. This is a very important part of the liver. It does occur naturally, and usually, many times I've asked questions about the effect, and I don't think that I really got to do a lot of this last semester because we were on time. So maybe I'll try to work it in. I don't know if this chapter or the other chapter that we'll do on fats. This is the breakdown fats, but maybe when we build fats up, about how diet plays a role in this, and statin drugs and things like that. All right. And so I don't know how the pictures will show up. Let's see. Oh, they show up pretty good. And so this is a major problem. So we can see the healthy liver, which whatever that color is, it's a liver color, versus fatty liver, which is also called. Does anyone know what the technical term? Which I probably wouldn't be able to spell it right. I'll try. Someone may be able to Google it. I think it's spelled steatosis. Nope, I already misspelled it. I think it's spelled this way. Steatosis. Steatotic liver. Oh, good. All right, so which is fatty liver disease, essentially. And it can get really, really nasty. It does look yellow when you get lipids. There are a couple of major problems. Like what's one way to get fatty liver disease? Probably in the United States. Well, maybe not necessarily. I was going to say probably number one cause of the United States, but I don't know that to be true. It's a major cause in the United States. I know for some countries, it is the number one cause of fatty liver disease. I mean, it's the consumption of one particular thing. That's alcohol. So there's alcoholic fatty liver disease, and then there's one called non-alcoholic fatty liver disease, which can be due to diets. It also can be due to metabolic problems. And so if you just eat too much fat, too many carbohydrates, you can convert your liver to fatty liver and start having steatosis. But that's why I say I don't know for us if the number one cause is just due to alcoholic consumption or not, or alcohol consumption I should say or not, but for some countries I know it is. And it can start to bloat, and like one time when the autopsies I went to see, someone had fatty liver so bad that their diaphragm had pushed on their liver so hard that it left indentations. It's like it had eroded, like it was like almost like a fossil. It left like a little imprint where your diaphragm has to go back and forth. So it had left impressions throughout there. Because the liver cannot go up, so it's going to have to go someplace. And then finally, we've got the exogenous, which for our Western diet typically can be a major concern. And those numbers are definitely outdated. I don't remember. I got them from the government website, but those have been outdated for some time. I'd have to look to see what it is for the major fats consumed. Of course, there's been a big push to be trans fat free, and so because they are, trans fats were only incorporated in relatively recent history, like in this last century. Why did they start putting trans fats in foods?
To make them last longer?
Yes. They do. They have much better shelf life. Okay, and what's the code words to have whenever some foods, like how can you tell if a food has trans fat in it? Like what's the code word, the way that the advertising agencies usually get around it? There's a term that they use. This is really technical. What? Partially dehydrogenated, right? Because what is a trans fat? Hydrogen's been added to it? Like, what is trans? It's a double bond. And so, and what kind of double bond is it? For a trans fat, what kind of double bond is it? Trans. Okay, and so that's why it's going to look something like this. What's that supposed to be a negative charge? Whoops. This is really sloppy. That would be a trans fat, whereas normally double bonds are cis, and so it causes kinks. So the more cis you have, the kinkier it gets, that kind of thing. But, and like I said, there's been a big push. It started, I don't know, in the last 10 years or so, that certain municipalities first outlawed or put a ban on trans fats because it is relatively easy to avoid. Okay, and so now more and more places are going trans fat free on their deep frying, but they still are available. But anytime, like with margarine or things like that, when you ever read it, it says it's partially dehydrogenated oils. That's just a fancy term for saying it's got trans fat. Oh, this is just a little picture. This is actually from last semester, so I included here to show you what we're talking about. These are just, and I didn't have you memorize like the common names and everything like that. I do expect you just once again to go over and just look at the kind of nomenclature that's used. Remember, for example, if it says like 16, 0, that means it's got 16 carbons and no double bonds. Versus if it says something like 16, 1, delta 9, that would mean that's 16 carbons, it's got one double bond, and it's at the 9th position, between carbons 9 and 10. Okay, and so that kind of thing. But you can see here, hopefully, that as you know, this one's called a saturated fat, because it's completely hydrogenated. It's all single bonds. And then this one, this is oleic acid, which has a single cis bond, so it causes quite the kink. And then we have linoleic, which has 1, 2, and then it goes on and on to where we know arachidonic, which has about 4 or 5. 4. And so it's kind of hard to tell, but it almost looks like a little corkscrew. This is glycerol, and then a triglyceride, all that it is just the esterification of glycerol. So we have an ester hanging off of each one of these. And even those that are saturated, as you can see here, it gets a little splayed because of the fact that you're limited by that glycerol backbone. One other thing is, I just wanted to remind you, is that these fats are not used, if you remember, they are not used in your membrane, your cell membrane, because those are phospholipids and various derivatives, and sphingolipids. These are really totally used for energy storage. Okay. Now, diacylglycerol also can be used as which is just where one of these has been replaced with an alcohol. So you don't have two fatty acids. That is also a second messenger for certain signal cascades. Okay. I really want to point this out in the fact that, sometimes I call them sometimes they're called tags. Triglycerides and triacylglycerols are the same thing, or it's called TAG. Okay. They are the principal energy form for us because you can see for every glucose, 1 mole of glucose, you only get 16 kilojoules per mole of energy, whereas palmitic acid, which is a common, 16 carbon containing fatty acid, you get almost 40. You get negative 38.9. So you get so much more. And the reason why is we're going to be oxidizing every single one of these carbons. Well, except for the very last one. Because it's acyl-CoA. So every group of 2 carbons gets oxidized. Okay, and so, all right. Now we're going to start talking about how, so this should be a review, hopefully, from anatomy and physiology. My goal. So I usually go over this pretty fast, this part. The role of where we get our fats. Okay, so just to review, the fats are absorbed by your small intestine. Okay, it's not by your stomach. Your stomach doesn't really do a lot of absorption. It does some medicinal absorption, but doesn't really do a lot of absorption. So it's your small intestine that's the major organ that's going to help you absorb that. What's primarily absorbed by the large intestine? Yeah, it should look at liquid, your water, right? And you're going to be forming your bolus. And so that's why if that gets out of whack, you get diarrhea because more liquid escapes from your anus, right? So that's why it's primarily for water absorption, whereas the small intestine does your other nutrient absorption. Okay, however, one of the problems is since fat is insoluble, or almost all fat is insoluble, you have to do what's called emulsification. It's got to be emulsified first before it can be absorbed. And this is a term, emulsifiers, that we use in medicinal chemistry too. What does it mean if something is emulsified? Like they use it sometimes in cooking. They'll talk about emulsion, an emulsion blender. It's fancy, but what does it mean? What's the number one characteristic of fats? What's their overall chemical characteristic? They are hydrophobic. Are we hydrophobic? No. So our bloodstream and things is hydrophilic. So we have to have some way. This is definitely an oversimplification. We have to have some way of getting something that's hydrophobic to be able to be absorbed into your bloodstream. So one way to do that is to deliberately put something around it, that's charged, that's amphiphilic, that could possibly have a hydrophobic end and a hydrophilic end. Okay, so we're like soap, because soaps are emulsifiers in that sense. Okay, pardon? The M-I-S-C. Oh, miscible. Something is immiscible versus, immiscible means it wouldn't be able to pass. Yep. Okay. So we're going to go through this. This, like I said, should be a review from good old AMP. And we're going to go into greater detail in chapter 21. Chapter 21. All right, so we've digested, we've eaten our fats, okay? Then what happens here, of course, there is hydrolysis that can occur in the stomach, start to break it down, but we can't absorb it, right? It's just a bunch of hydrophobic things. The emulsifiers that typically use, that our body uses, are going to be bile salts, okay? So that's from the gallbladder. This is one of the reasons why people with gallbladder problems typically have more issues with digesting fatty foods. You can live without your gallbladder. It runs in my family. Multiple people in my family have to have their gallbladders removed. But then many times they have to watch out, be careful with their diet, because if they have things that are too high in fat, it causes diarrhea, it causes major gastric problems. Gastrointestinal problems, I should say. All right, but the gallbladder is going to produce the bile salts, and release them through the bile duct down here. And in the small intestines, they're going to form these mixed micelles, okay, which if you remember from micelles, just means that they're going to form that little, what's called a micelle, that little vesicle-looking thing around it to make the fat more water-soluble than what it was before, okay? Now, once inside, you can actually have lipases, which that's a new I've mentioned once before, but those are classes of enzymes. So that's another thing. We have proteases, which proteases break down proteins. Nucleases break down nucleotides, like DNA and RNA. And then lipases break down lipids, like your fats. And so there are specific lipases that will break down the triacylglycerols, okay, once you're inside there. Okay, then they get absorbed through the mucosa and converted into the various things that need to be converted into, okay? And so we'll talk a little bit in greater detail in chapter 21 on the roles of apolipoprotein C's and B's and things like that. But ultimately, these get incorporated into what's called anything from chylomicrons to, depending upon their levels, later on we'll talk about like LDL and HLDL and VLDLs and all those, like your quote-unquote good versus bad cholesterols. But the chylomicrons themselves are the ones that typically do just free fatty acids, the triglycerides. Okay. It gets traveled through the lymphatic system and the bloodstream to whatever tissues need it, and then once it does, then we're going to have another lipase that's going to come through and help break it all apart in order for it to go and be stored, either in a adipocyte, be stored for later storage, or it could actually be, if you need it for energy right there, it can be oxidized for fuel. Okay. All right. Okay, so just in general, to review what I just said, we have chylomicrons, which they primarily do your tags. There are some specific proteins that are incorporated along with those. Now, sometimes I'll talk about apo, whatever. Apo, what does that prefix mean? If it's apo, it means without. So if it's an apo enzyme, it means it's without something that needs to be active. An apolipoprotein means it's without its like lipids. Okay. And then the lipoproteins themselves go all the way from VLDLs to HLDLs. Oh, right. And so this is just an example of one of these lipoprotein complex. Oops. So different proteins can be distributed on the cell. It's not on the cell, on the outside of these complexes in order for them to be recognized with different things. And then we can see here that we've got primarily the tags on the inside. There are some cholesterol esters, which are just like it sounds. It's cholesterol that's been esterified in order to make the cholesterol even more hydrophobic than what it was before. Okay, and then there's some cholesterol here that's incorporated. And the percentage of protein to lipids is what the difference is between the HDL and the LDL. And once again, we'll go into greater detail of that in a different chapter when we talk about those in greater detail. I'm going to go ahead and end here because I'll show you the preview. We're going to actually talk about what hormones, and this is a major flow chart that I go through where we go step by step on like what hormones play important parts. Okay.